Okay, welcome back. So, have you in the meantime, have you come to any ideas about this behaviors of your agents or components? Okay, if no? Okay, that's fine. Okay, let's go on. Yeah. Okay, rapid prototyping. So, how to prototype your products. As I said, part of the reason why I'm talking about software agents here is that this is actually the super highway fast track to prototyping. Because why? Because I mean, with software agents, I mean, you can also simulate humans in the system. And otherwise, it might be complicated. I mean, to have all the humans, I mean, in place to demonstrate your system. But with software agents, you can put up some humans. I mean, you can just mimic some humans because, you know, there are many artificial intelligence techniques that can be embodied in software agents that make software agents to look almost as real humans. I mean, regarding their behavior, but also regarding their appearance. So you can have some talking avatars on your screen that also behave as real humans. And I'm not here actually talking about Second Life, because, you know, in the Second Life, these avatars, I mean, they are all actually, they are directed by humans. I mean, they are not independent, they are not autonomous, but they could be made autonomous. Well, 2 years ago, when I taught my course, Agent-Oriented Modeling and Multi-Agent Systems, then one of the exercises I gave to my students was to come up with or to model a best version of Second Life, where avatars would be autonomous, where you could actually delegate your avatar with some tasks, so that your avatar should go somewhere and should actually should make acquaintance to with someone, and should be engaged in certain activities. So all this is possible, and all this can be programmed as well by means of Second Life. And actually, the students came up with brilliant ideas. I mean, how this could be done. So this is why I'm actually here promoting software agents for prototyping your product ideas. Now the question is, I mean, how could it be done in technical terms? But before going to that definition again, so what is rapid prototyping? So I would define it as implementing a proof of concept prototypes in an agile way by directly mapping the modeling constructs to the constructs of a scripting or programming environment. So what do I mean by this direct mapping? Well, we have gone through different models here. So we started with goal models, then we created decided roles, created role models, organization model, domain model for analysis. After that, we decided the types of agents. We decided acquaintances between these agents. We decided the knowledge by these agents. And by now, we already, let's assume at least, we have decided behaviors by these agents. So these are all modeling constructs. And now they should be easily mappable to implementation constructs of some scripting or programming environment. Of course, this modeling stuff here, this sounds as an awful lot of work, but it's actually not true. I mean, all these different models, they feed into each other. They are related to each other. So this is a very natural process. So maybe within this short course, you didn't quite perceive it as a natural, coherent process, but all these model types are related through the viewpoint framework. And in this sense, it is quite easy to map one model to another, and to map models to the implementation constructs of some programming environment, like Jade, for example, that I'm going to talk about today. And further on, this can be automated, and this is actually one of the activities in which me and my research group are engaged now. how to automate the development of fast prototypes, in the sense that you create your models, and then you elaborate your models, and from these models at least the backbone of your prototype will be generated. So this is one of my research directions, and this is directly related to innovation. I mean, how to make it easier for innovators to come up with rapid prototypes of their system as early as possible. Here I also have mentioned the term agile, and this is very important actually, even though I haven't emphasized it too much here, but basically you do not need to do all your models. You do not need to be complete. You do not need to be perfect in order to start prototyping. But you can take just one branch of a goal model, for example, and develop for that branch other types of models. Decide roles for that branch, decide relationships between roles, decide types of agents, their acquaintances, their knowledge and behaviors, and then implement it right away, or generate the implementation right away. So this is an agile approach that I'm also investigating. One of my PhD students actually is doing work in this direction, how to apply agent-oriented modeling in agile software engineering in order to produce software as early as possible. And my claim here is that agents facilitate rapid prototyping exactly because of the reasons I explained earlier, that with agents we can also mimic humans. So we do not need the humans to participate in a demonstration of a prototype, but we can actually simulate these humans by software agents. So here is where we are right now. So we are talking about prototyping, about interaction prototyping, information prototyping, and behavior prototyping. So they all form different perspectives of prototyping. So because we need to prototype, first of all, interactions between these different agents or components of our system. We need to prototype the information they possess. We need to prototype their behaviors. Let's go to intruder detection case study. So another case study I'm going to briefly introduce. And why is it important here is because a video shot I'm going to show you pretty soon is about prototyping this case study. So it is about how group of students at the University of Melbourne, how they prototyped the case study they had implemented based on agent-oriented model. So it's exactly the same process I was referring to earlier, that we model our system and then we map these models to rapid prototypes. But first of all, so that you would understand what is going on in that video shot, just a short description of the case study. So here is the goal model. And it is about handling an intruder in a smart home. The main goal is handle intruder. So this is the purpose of that subsystem. Well, it was broader than that. It wasn't just about intruder handling. It was about intelligent home in general, about intelligent lifestyles, but intruder handling was one subsystem. And by the way, another interesting subsystem was just greeting the owner of the smart home. If the owner comes home, then the owner expects to be appropriately greeted by the system. So this is sort of, I would say, like a hello world version for agents. So you enter home, and then your agent of your smart home should greet you in an appropriate way. What do I mean by an inappropriate way? Is that, for example, if you come in a happy mood, then the agent should somehow perceive it and then should greet you in a very kind of elevated voice tone, elevated kind of pitch of the voice. But if you are sad, or if something sad has happened in your family, then the agent should offer comfort and should use the corresponding tone of voice. Or, for example, if you return from jogging, then the agent could ask, I mean, how are you? I mean, do you feel fresh now? I mean, after doing this exercise. So it is this greeting by an agent is not as simple as it seems, but it should be context dependent. It should depend on the context of giving that greeting to the owner or to someone else. Yep.
Actually, this greeting system should encapsulate the intruder detections, because
yes,
you detect the person who you are supposed to greet.
Yes, yes.
So you need to know.
Yes, yes, exactly. Yeah, good remark. I mean, they are definitely closely intertwined. I mean, the greeting system and the intruder detection. And this is, of course, a bit simplified. I mean, and it isn't fully integrated because it was a student project. So here, I mean, the greeting subsystem and intruder detection subsystem, they have been addressed in pretty much in isolation from each other. But you are absolutely right. I mean, they should be intimately connected. Yes, merged even, yes. So, handle intruder is the purpose of this subsystem. There is an important quality goal saying that the greeting should, saying that the intruder detection subsystem should give an appropriate and timely response to the intruder detected. Now, there are roles. This is an interesting role, isn't it? Intruder. I think it's the name is not quite right. It should be potential intruder. Because, well, how does the system know, I mean, in the first place, who is an intruder, I mean, and who is a visitor? So potential intruder would be a better name, but definitely we need this kind of role in our system. Intruder. Then there is security manager, who is responsible for managing security in the house. So it is not just about detecting intruders, but it is about windows and doors and garden and all these sensors that you mentioned in the description of your case study. I mean, how you actually protect the perimeter of your property. And then there is one more role, evaluator. And evaluator, why is it needed?
Is it one that have rules of what is bad or what is good? No?
In a way, yes. Yes.
Like if a window is opened but the house is actually closed, then it's probably the alarm. No?
Well, actually, the idea for evaluator here is that an agent playing the evaluator role can be a human, can be a software agent, is the one who evaluates the intruder detection. For example, if there is an intruder has been detected, after that police has been summoned, and then the intruder has been arrested, then someone needs to evaluate that process, and in order to learn from it and then make conclusions about how similar incidents should be handled in the future. So this is the idea. There needs to be someone evaluating, and usually it's the case when you have something has happened. I mean, so your house has been broken into, for example. Then you always evaluate this, and you actually try to understand, I mean, how this could have been avoided, for example. So there is always someone doing evaluation.
Is it like a detective?
Well, not quite. Maybe we don't always need a detective, but it can, of course, the owner can play the evaluator role as well. Yeah. So the same, I mean, the same person can play several roles. So it can be the same human agent playing the owner role and the evaluator role. So what is going on here? So the sub goals are notice. I mean, potential intruders should be noticed timely, in a timely manner, is represented by this quality goal. So functional goal notice, quality goal timely notice. Identify, the potential intruder should be identified. Maybe it's a family member, maybe it's a visitor, maybe it's a plumber, maybe it's an electrician. So somehow the system should be able to recognize the person and understand, I mean, who is the person and why is the person there. And the quality goal pertaining to the functional goal identifies accurate identification. Then the next sub-goal is respond. And a respond sub-goal in turn consists of consists of three third level sub-goals. Inform police, or it can be security company. Maybe it's a bit exaggerated to inform police right away. I mean, it could be a security company. Inform security company. Here is the role for police or security company. Inform visitors. Inform visitors scheduled to be at the house at that time, because there is something going on in the house. I mean, it's not safe to go there. So the visitors should be informed that please stay away. Something is going on. We will sort out the situation, but until it has been sorted out, please stay away. Then there are two more roles here. Of course, the role of visitor, someone playing the role of visitor, and scheduler. So probably a software agent playing the role of scheduler, that scheduler is aware of different activities in the house, is aware of the people who are supposed to be there, is aware of the visitors, is aware of technicians, plumbers, electricians, and so on. And then there is inform owner sub-goal. So we should inform the owner about the situation, that there is something going on in your house. Please pay attention to that. So this is the goal model for this intruder handling scenario. I know it's a bit simplistic. I mean, maybe not real, in completely real, but this is what this team of students came up at the University of Melbourne, and it was good for that purpose. So for real life, I mean, things are handled a bit differently, but still in a similar way. Here is the domain model for intruder detection. You can see these domain entities like person description. What is meant here is it is the description of the person according to the photo taken by a security camera, or according to a video stream from a security camera. So here an attempt is made to recognize the person. Is it necessary or not? I'm not sure. So maybe it's not reliable enough to recognize the person right away, but this is the approach the students took in that particular case study. So a person description, then a person description describes intruder, well, because it's kind of technical description received from a camera. Describes intruder or potential intruder. Then we have house schedule, and house schedule is created by owner. Then house schedule, then we have a security manager, and security manager analyzes that person description, but when doing so it consults a house schedule, because house schedule contains information about the people who should be there at the given time, like family members or plumbers, electricians, and so on. And then also security manager warns visitors. When we go up, then we see that we have a domain entity for a suspect, and police knows about suspects. So suspects are like different. This is a database that police has about different criminal elements, so to say. I mean, people, who have actually committed some bad deeds, and that's why they have been included in the database of suspects by police. And the person description may identify a suspect. So a person description may identify a concrete person, who is included in the database by police, and who obviously has a criminal past. So this is the domain model for intruder detection.
But this system doesn't care about dogs, cats, birds that often actually break the rules of security.
Yeah, they are not included here. Yes, no, this is about people. Well, pets. What we assume here is that this camera maybe is smart enough, or the sensor is smart enough to distinguish between humans and pets. Face recognition. Yes. Face recognition. Even though, as you will see, the technology that is used here is pretty outdated. Because this case study was made several years ago. But that is, of course, it's actually, to tell you the truth, it is not able to distinguish between pets and humans.
More. Not yet.
Yeah, not yet. Yeah.
More than the kids, actually.
Yeah.
You know, that until a certain age, for example, the PIR sensors don't
yes.
small age.
Yeah. Yeah, but there may be, by now there may be such a technology available actually that enables to distinguish between pets and humans. But here it's actually not available, but we pretend it is available. Yeah. Because it's, after all, it was actually a case study made by students, made by actually a group of students. So there were like around 10 students. So that's why they were able to actually model it, design it, implement it, and also prototype it, as you will soon see, act it out. Yeah. Here is the interaction model for intruder detection. So this is a kind of a nice fresh up for our modeling part. So we go through almost all models here. What is going on here? So this is a person playing the role of a potential intruder. This is a move made by that person, physical move, I mean, some kind of physical move. And that physical move is perceived by security manager, I mean actually by security agent playing the role of security manager through some sensors. So, you know, I mean, I make a move, there is a camera who actually recognizes the move, and then this causes alert. So this is the way we model it. This is the way we conceptualize it here. This is the first message in this interaction model. What will happen after that? So after that, a message intruder detected will actually be sent to a police agent. Well, actually, it's I mean, this gives you a false impression that this is done right away after perceiving some potential intruder. No, as you will see in the next diagram, I mean, there is a behavior inside here that checks if that potential intruder is someone who actually should be there, like a family member or plumber, electrician, and so on. And only if the person in question is not someone who should be there, the message is sent to the police or security company. So this is message 2 in the interaction diagram. Then message 3 goes to the visitor who is scheduled to go there pretty soon. So message 3, and the content of this message is that intruder is in the house, please stay away. You will see it also in the demonstration how it actually was acted out. And here message 4 is to the owner, and the content of the message is intruder is in the house, and police has been alerted and visitors have been warned. So these are the interactions in that case study. And here is the behavior I was referring to, the behavior of a security agent. And again, here, I mean, the behavior started by that move by a potential intruder. It's a physical action, like physical move. Then this rule R1 starts activity handle intruder. Then this activity handle intruder has sub-activity identify intruder. And that sub-activity includes the rule R2. And the rule R2 checks if the person is known. So this is a condition for this rule R2 that checks if the person is known for the home security system. And if the person is not known, so this is the meaning of this arrow. If this is not true, if the condition is not true, if the person is not known, then a response sub-activity is started. And the response sub-activity consists of 3 sub-activities in turn. They are inform police, you see, and the action included by this activity is inform police that intruder is detected, then lock the doors and windows so that the intruder won't actually get away. This is an interesting one, isn't it? So lock the doors and windows in case they are not locked already.
Put gas inside.
Yeah, so because we want to catch.
There was a film on television.
Yeah.
In England, and there was a fella locked inside the house, all the locks shut, and the perimeter of the house was electrified.
Yes.
Until the police came.
Yes. Exactly. It's realistic, as you can see now. Yes, of course, we should do it. We want to catch these intruders so that they won't do it again. Yes. Then inform visitors. so that they will stay away. And for the informing, you see, there is a kind of procedure call here from scheduler. Obviously, scheduler is not implemented as a software agent. You see, it is a service actually. So I'm far from saying that all roles they have to be implemented as software agents. No, some roles should be implemented as services or some other kinds of software components. This is the case here. Scheduler has been implemented as a service. So here we ask from that service the schedule. And the intent of this activity is to find out if someone has been scheduled to be there at that moment of time. And if it's true, then it's all right. Then this alert should be cancelled. And finally, inform the owner that police has been alerted and visitors have been warned. And in addition to this, this behavior of a security agent and these interactions, you can also see some elements of knowledge by agents here, because this is a combined model. It is not just a behavior model, but it actually is a combination of interaction model, a behavior model, and knowledge model, which can be good in some cases, to combine these models so that we won't need to actually present different models, understand different models, but everything is just included in one model. So this is a part of the knowledge model. This is the person description that describes a potential intruder, and that is actually shared knowledge between police and security agent because of this message here. Well, we send a person description. This is how it becomes shared knowledge. And the police then matches it, this person description against the database of suspects. And here is also a kind of internal database for the house of different people, different family members, different visitors. The kind of negative feature of this system is that it requires all family members or all potential visitors to actually present their face for recognition in advance. So they should have, there should be photos taken of different people in the system so that the system would work properly. Okay, any questions about these models? These were models. And now we're going to that video. And please don't pay attention to the technology. I said it was made a couple of years ago, but the important is how this system was kind of acted out by students and prototyped. Yep, please, thank you. Okay, this is an intruder, intruding. Now, opening the door. Okay. Here we are, looking for something valuable. Okay, the camera, quite old-fashioned, but actually there is a working technology behind it. It's not just a movie, but it's all. It's all working. It's all actually real life. Okay, this is. It is the owner, and now the system asks if the owner knows the person. The answer is no, I don't know the person, and continues on, goes on with her activities. So these are the visitors scheduled to go there. An intruder is at Jane's house, stay away. Okay, so no visit today. No. Okay, the owner again. Okay, another message coming in. The police are on the way. Okay, good, everything's under control. Okay. No worries here. Australian attitude, no worries. Police? Police is nearby. Looks criminal. Is nearby now? It's close to the house I worked in Melbourne. Actually. Yeah. Okay, the intruder is on the balcony, so very up-to-date information. Okay, and this intruder is arrested, so everything ends well. So it was amusing, but actually, again, I repeat that there was a working technology behind it. There were software agents, there were sensors, there was actually a pool of sensors. It was quite a complicated system. It was a hybrid system, not purely peer-to-peer, but a hybrid system. There was server, there was a pool of sensors. The server took care of those pool of sensors. The server took care of those sensors, but there were also agents representing the police and representing this smart house. And there were these portable digital assistants. Okay, now we're going right away to the second case study, and this is related. Actually, the case study has been explained to you already. This is what Professor Leon Sterling did via video conference. It's a case study about interactions between grandchildren and grandparents over distance. And this is very relevant for Australia, because you know, in Australia it's often the case that grandchildren live in UK, for example, grandparents live in Australia, or the other way around. Grandchildren live in Australia, grandparents live in Estonia, for example. So somehow with these grandchildren, I mean, they are deprived of many of those usual communication patterns that occur between grandchildren and grandparents. So I'm not talking about exchanging emails. Of course, they can do it. I'm not talking about Skype, talking over Skype or chatting, but I'm talking about more emotional ways of interactions that where, for example, photos, videos are involved, where people can share memories, where they can actually relate to each other at an emotional level. And this is what Professor Leon Sterling was talking about that case study, about the different ways how this has been made possible, about ethnographic studies that have been made, interdisciplinary studies related to psychology, social sciences. So all this is actually interdisciplinary research work that has made possible such product prototypes that you're going to see now. And that is, I mean, how this product, not really product, but let's say a proof of concept prototype for intergenerational play was tried out in Melbourne. And again, it is a prototype, it is not a full product, but by now it may have been developed into a full product because it's a great idea. So let's go to the second video clip. That is the third one. Yes, that one. Yep, and that comes with voice. Yeah.
Soon be able to keep in better contact using new touchscreen technology called the Collage, created by researchers at the University of Melbourne. Sending messages. By sending photos and text messages to a central computer, users at each end keep up with the day-to-day activities of their family members.
The project has to do with using technology to enhance the quality of life.
A unique element of the Collage system is that users can interact with the images and the text messages as they scroll down the screen.
Touch them to make them bigger, and when I don't want them, I'll jump along the side.
The Collage system has been developed by the Interaction Design Group in the Department of Information Systems at the University of Melbourne. It has been developed with support by Nokia and the Smart Internet Technologies CRC.
In the not too distant future, families will have some sort of digital display in their home, whether it be for television or for broadband or for cable TV. It's likely they'll have some sort of display in their home.
Although their grandparents only live nearby, the system improved the family's communication, particularly with the children.
This was more visual and the kids took more of an interest in having the images up there in front of them, talking on the phone. They get a bit bored and you can't get much information out of them, but this way it captured their interest a lot more with moving the photographs.
The Collage system would really help families that are separated by distance.
You did a Lego, right? I said the Lego one, it's the new Lego. I did see those too, and I saw your one too.
It also got the grandparents up to speed with the latest digital technologies.
My mum has a mobile phone, and she used it just for basic calls, but since doing this, she's become like texting all the time and finds it a lot easier.
I've had a comment from someone who said, "You can text." So I felt very ancient but very clever. Well, I thought it was great fun because the communication was instant and therefore we could see what the children were doing.
The University of Melbourne is one of the foremost groups in the world leading in the development of this communication system.
Okay. So this is what was done with antiquated technology. And can you imagine what could be done with smartphones? I mean, in the same kind of direction. So because that was done several years ago, but that is an example of a social application where actually different new technologies, including agent technology, were applied. So I hope it gave you maybe some good ideas actually about what kind of products would be needed. I mean, it doesn't have to be about relationships between grandparents and grandchildren, but in general. Okay, and now, so I promised to become more technical. Someone asked me about the platforms, and the one platform I'm going to shortly introduce here until lunch, and that is Jade. Java Agent Development Environment, which is good for actually developing rapid prototypes of your product ideas. Here again we come back to these different kinds of systems: pure peer-to-peer, client-server, and hybrid peer-to-peer. And the Jade platform follows hybrid peer-to-peer, meaning that the nodes interact directly with each other, but for some operations, like for example finding other nodes, a server is used. And this makes sense. This is the so-called yellow pages approach, where we need yellow pages for finding other companies. In the same way, yellow pages here are used for finding other nodes, other agents in that platform. And actually, about peer-to-peer systems, most of you here have come up with product ideas that are about social applications. There are applications that somehow help people to interact, help to make right decisions. And I think that peer-to-peer applications or hybrid peer-to-peer applications might be much more appropriate for this purpose as compared to client-server systems. And of course, many social applications like Facebook, they are essentially client-server systems. And it works, but I think that you should also keep in mind the peer-to-peer approaches if you want to come up with really efficient social information systems. And a good example is Skype. Because at the time when Skype was invented essentially by two Estonians, already then the client-server systems were predominant ones. But despite this overall direction where the world was going, they were thinking in a different way. So they were able to come up with a totally different solution, peer-to-peer solution, that became very successful because they didn't follow mainstream. So that's why my advice for you is that do not always follow mainstream. But also pay attention to some niche technologies if you want to really come up with really original and unique and useful products. So what is Jade then? Well, it is a platform that is distributed that can be split among several hosts. It has a Java application programmer's interface, which means that the programming here is essentially Java programming. And it has a graphical user interface that enables to manage several agents from the same remote management agent. I will show a snapshot of that graphical user interface a bit later on. and it is actually based on the FIPA specifications, and FIPA is an organization that has attempted to standardize agent stuff. I mean, standardize agent communication languages, their interaction protocols, yellow pages mechanisms, and so on. And this is where you can download Jade. It is free, so everyone can download and play with it. Here is how it looks like. There are different hosts, like your laptops here, for example. One host can run several Jade agents. These are those application agents here. And, on each host there is one container, and one of the containers has to be a main container, and this is the one where the multi-agent system is managed, and the others are just agent containers. In other words, here this host 1 has this Jade main container running, and here is where the system is managed from. Here where the yellow pages reside here, and also where you can actually start from the user interface. You can start new agents and stop new agents. And here, and as I explained to you earlier, I mean, here is the lower level. So just pretty much like in case of an email client as an agent, the email client as an agent would be at that level, and here is all the lower level stuff that actually that agent doesn't need to care about, or actually that the human using the agent doesn't need to be care about, but it is somewhere here, like this network protocol stack. Now about agent lifecycle in Jade. So now I'm talking about software agents, of course, not human agents. So first of all, an agent is created. Well, it is in an unknown state, well, meaning that the agent doesn't exist. It is created, then an agent enters the state initiated. So then agent becomes initiated. Then after the invoke action, the agent becomes active. Now the agent can be actually can be sent to the waiting state by executing the wait action. Then after that the agent is in the waiting state, and the agent can be woken up by wake up action, so that it returns from the waiting state to the active state. Then what it means is actually that in the waiting state an agent waits for messages to be received. So this is the meaning of the waiting state. An agent just sits there in a passive mode and waits for messages to be received. And if a message arrives, then the agent is woken up and becomes active again. An agent can also be suspended, meaning that an agent can be temporarily stopped. It's not the same as waiting, because if an agent is temporarily stopped by performing the suspend action, then it is not able to receive messages. But if an agent has been taken to the waiting state by performing the wait action, then it is waiting for messages. So this is the difference. So we can suspend an agent, then it will be in the suspended state, but then after that we have to explicitly resume the agent so that it would become active again. And then there is an interesting state transit, and this is related to mobile agents, because Jade agents can also move between platforms like viruses. Of course, they are not viruses, but they have the capability to move from one computer to another. And this is done by executing the move action, and after the move action has been executed with appropriate parameters specifying the destination for the agent, then the agent is in the transit state, and in the transit state it arrives some other computer, and then it is executed on that other computer and becomes active again on a different host computer. So this is the idea for Jade. It's an agent lifecycle for Jade. So, any questions about this? Okay, and now we're becoming really technical, how you create and terminate Jade agents. So this is nothing but Java programming. I don't know how many of you are familiar with Java programming. couple of people. Yeah. So basically, what is done here? Well, an agent is created by executing the setup method, and here this is about the simulation of it for Tamagotchis. This is about actually the idea here is to come up with a rapid prototype for Tamagotchis. So the assumption is that the Tamagotchi doesn't exist. Someone has come up with a great idea for Tamagotchi and has modeled this product, and now is trying to prototype the product in order to show to venture capitalists and ask, does it make sense? So this is now about simulating Tamagotchis. I will show you a screenshot also about this, how this simulation looks like. But here you see the present list is actually is filled with the different presents: food, chocolate, toy, the presents that a Tamagotchi can give to another Tamagotchi. The user interface is created for Tamagotchi. The local environment is created. The Tamagotchi shell is created. I mean, this box here. I mean, the simulation of this box, I mean, because, well, as I said, I mean, we assume here that this Tamagotchi doesn't exist. Well, we need to simulate it somehow, this Tamagotchi, including its shell, including the digital bed inside it by means of software. So here we simulate the creation of Tamagotchi shell, creation of user interface. I mean, this kind of user interface with simulation of this user interface. And here this agent is taken down, or agent is Tamagotchi is finished here, is terminated. Okay, and now an important part of JADE is formed by concurrent tasks. So a JADE agent must be able to carry out several concurrent tasks in response to different external events. So like events in the environment, an agent perceives these events and then starts one or another concurrent task that is called the behavior of an agent. And every JADE agent is composed of just one execution thread. The concurrent tasks are modeled as instances of the class JADE core behaviors behavior. So just one execution thread, and here you see how it works. It is just one thread. So the agent starts with executing a setup method. Setup, here the agent is initialized and initial behaviors are added if needed. Then after that, there is a check if agent has been killed by executing the do delete method. And this means that has the agent been, for some reason or another, has the agent been terminated? And if not, then we proceed. This is next. No, and now next behavior is retrieved from the pool of active behaviors. So now I'm referring here to the agent as a whole, just one agent, not to individual behaviors, but just how one agent works, how one agent behaves. It is one thread, but several behaviors. And these behaviors are, of course, they are related to different activities that an agent performs. They may not be related to just one process, but an agent may actually do different things at the same time, may be engaged in different systems at the same time. So the next behavior from the pool of active behaviors is retrieved, and now after this has been done, the action method of that behavior is executed. And this is printed in red because a programmer now has to fill in that method. The programmer has to decide what that agent is about to do. So this is in red. And also this done is in red. The next actually option, this is an option, this is a choice. The next, this choice node is also printed in red because it is now up to the programmer to actually define what it means that the given behavior is done, that there is no need to execute the given behavior again. And if it is done, then the current behavior is removed from the pool of active behaviors. If not, then we return here and it all starts all over again. We check if agent has been killed. If not, we retrieve the next behavior of that agent. and then we actually perform the action method that specifies what that behavior is about to do for the agent, and then we check if the behavior is finished, and if not, we go back here again. If yes, then we remove this behavior from the pool of active behaviors. And of course here, if about this choice, if an agent has been killed, then we go to the takedown method that is specified the programmer. The exact procedure to be taken is specified by the programmer, but the meaning is always the same, that the takedown terminates the agent, but the user, the programmer, can just describe what messages are issued when it is done, for example. That, like you saw here, for example, this is the message that is printed out, Tamagotchi terminating. So, but takedown, the meaning of takedown is predefined. So, any questions about this? So basically, it's the Java programming, and here is how we define behavior. So this was about, how an agent executes, how we retrieve behaviors and execute these behaviors, but this behavior should be somehow defined. And the part of defining a behavior involves this executing this action method. And this is how we define a behavior. We extend the behavior class of the Jade environment, and here is the action method I mentioned. So, and here we actually we program something here for our agent. So we describe the activities to be performed by our agent. And here is this done method, and this is up to the programmer to write something here. So what is wrong with this behavior? Those of you who are familiar with Java programming, is there anything wrong with this behavior?
Actually, according to the Jade, if I'm not mistaken, behavior is abstract class, you can't extend it. You need to implement specific behaviors like simple behavior or parallel behavior.
Extends,
you can...
yeah, you may be right.
Implement.
Yeah, you may be right actually. Maybe there needs to be as a parallel behavior. I will come to that later. Next. Yes.
Parallel or
simple or parallel. Exactly. Yeah, I'm coming to this. Yeah. But is there something wrong? Anything wrong with this?
The wrong is while true, it will never be going out from the cycle.
Yes. Yeah. It never finishes. This behavior never finishes. External loop. So what basically this kind of agent will exhaust all of your resources, and then then you will end up with you need just to kill it. Yeah.
Your CPU will become
exactly. Yeah. This is exactly. Yep. Yes. Yeah, I think you are right. This is an abstract behavior, and these are hierarchical behaviors for Jade. This is the abstract behavior you were referring to, and you cannot extend it directly. Thank you. Yes. You have to extend. I think you have to extend those here.
Yeah, one of those.
Yes. Because this abstract behavior, there are subclasses: composite behavior, simple behavior, and simple behavior is divided in turn into one-shot behavior and cyclic behavior. One-shot behavior is a behavior that is actually executed just once, and cyclic behavior is executed as many times or is executed until its done method returns false. So this is what we saw here actually. Yes, basically this is the done method, and the cyclic behavior is executed until it returns false. And then the composite behavior is divided into sequential behavior, which consists of sequential sub-behaviors that are executed one after another, and parallel behavior that consists of parallel sub-behaviors that are executed in parallel to each other. And then there is a more complicated behavior, finite state machine behavior, which models a complex task whose subtasks correspond to the activities performed in the states of a finite state machine. So this is related to state machines, and this is becoming really complicated, but on the other hand, it enables one to do more sophisticated things and implement actually more actually clever systems. Okay, defining behaviors. Okay, this is the right way actually. My one-shot behavior extends one-shot behavior rather than abstract behavior. my cyclic behavior extends cyclic behavior rather than just abstract behavior. Yes. And again, we have to fill out this action method as programmers. Adding a behavior, how we add a behavior to an agent, an example is here. We add a behavior of mood checker here, and this can be done as a part of setup method. And why mood checker? Why do we need this mood checker? I mean, this is a behavior that checks the mood of an agent. Is it in a good mood or bad mood? So why do we need it? Well, we need it because these JADE agents they actually are by definition reactive, which means that we somehow need to actually simulate or compensate somehow the proactive behavior. So, and one way to do it is to have the behavior, cyclic behavior like this one, mood checker, that actually works in as a loop in cycle, and that behavior checks the mood of a Tamagotchi. So checks every, let's say, like every couple of minutes, checks the mood of a Tamagotchi, and if it discovers that the Tamagotchi is in a bad mood, then it actually instructs the Tamagotchi to send a message to its owner that I'm in a bad mood, please do something about it. So this is how we actually simulate proactive behavior in JADE. Some other agent platforms, they enable actually to explicitly program proactive behaviors. But unfortunately, this is not true for JADE. So here we add the behavior of a mood checker that checks the mood of a Tamagotchi in a loop. And here you can see cleanup operations for the agent again, which consist of printing a dismissal message that given Tamagotchi has been terminating. This is how sending messages happens from an agent. This is not about Tamagotchis. This is a more general example. But here, again, I mean, we can sort of remind ourselves about what we have learned so far. So what is done here? We create a message. The message is of the type inform. By this kind of message, one agent informs another agent of something. Then we add receiver. So a receiver is Peter here. We add language, English. We add ontology, weather forecast ontology. So an ontology is very important here. Ontology is something that both agents need to be aware of in order to successfully interact. So it is the common framework for understanding the world for both agents. So ontology is always a part of any agent message. Because we're talking about software agents. If it would be about humans, I mean, then I mean we have actually quite similar ontologies at least. But for software agents, ontologies need to be explicitly described. And here, this ontology that is referred to is weather forecast ontology. The content is that today it's raining. So of course this is like a sort of game here, but this is just to give you a kind of overall understanding, I mean, what the ontology is about. And here is another example where a message is sent to several receivers. It is about a call for proposals message that is sent to several agents, and each of them, those agents represents a different company, and then they receive this call for proposals message, and then they respond with proposals with quotes, and after that the buyer chooses one of those quotes, and then later on sends an order to that seller. So this is about how messages are sent in JADE. Receiving messages are much simpler. Well, as you may remember, what I told about asynchronous communication. In asynchronous communication, the messages to be received are always stored in a buffer. So if one agent sends a message to another agent, then that other agent stores the message in a buffer and then processes that message from the buffer at the time that it considers appropriate. So in synchronous communication, a message is processed right away. In asynchronous communication, a message is processed at the time that the receiving agent considers appropriate for that. And here, this is what is done actually. If there is a message, is the meaning of this expression, process the message. And this is now, there is a special receiving behavior that should actually check in a loop if there is a message. And if there is, the message should be processed. And actually, this needs to be done in a loop, of course, which is not shown here. Again, a little reminder about this behavior model of Tamagotchi. You remember that I just explained in the morning how the two Tamagotchis, or how a Tamagotchi expresses unhappiness, and how the owner instructs or asks her Tamagotchi to visit another Tamagotchi, how they connect, how the visit goes on, request visit, go to the friend's place, and then they give in a present and play that happens in a loop, and the presents are actually given as long as there are enough presents available. And finally, return home if the Tamagotchi is finally happy. If it's not yet happy, if it's still unhappy, then this activity, give a present and play, is repeated again. And now how it looks like in Jade. The simulation again, not the real Tamagotchi, but the simulation. So this is how it starts, this corresponding fragment of Jade. Here we just define the variables, like the variable for message. We construct the behavior, and here is where the actual implementation of the behavior starts. And then we create a sub-behavior, create a behavior request visit, actually create a sub-behavior request visit, add this sub-behavior, execute this sub-behavior, remove it because it's not needed, it's one-shot behavior, it's executed just one, because the first Tamagotchi asks the second one just once for a visit, for a permission to come for a visit. And then the local environment is retrieved here because it is needed for a visit. And here you will see how the visit happens. If there is a reply from another agent, please come. Oh, I forgot. Here also this sub-behavior here also includes sending a message to another agent with a request to come for a visit. And here, if the reply received to that request is please come, then the one Tamagotchi goes to the other Tamagotchi's environment, and if that was successful, so that in real world we connect these two Tamagotchis and one goes to the other one's environment, and this is what we're simulating here. If that was successful, then we inform the owner that the Tamagotchi is away from its shell, is away from its local environment, and we inform it by actually typing the appropriate message on the Tamagotchi's screen, away. You remember that one of the first slides I showed to you on Monday is where one Tamagotchi has left its local environment, has left home, and is playing with another Tamagotchi in the home local environment of that another Tamagotchi. And here we had a sub-behavior go into the friend's place, execute this sub-behavior, and here we check the Tamagotchi's happiness level. So this is actually what we do here is we do this thing here. We are checking if the Tamagotchi is still unhappy. And if it is still unhappy, then we create the behavior, give a present and play, add this behavior and execute this behavior and remove it. And if the Tamagotchi is still unhappy, we do it all over again. I mean, create this behavior, add it, execute it, and remove it. And finally, the Tamagotchi returns to its own shell, to its own local environment. So just an overview how it is programmed in Jade. And this is about blocking a behavior. It is about receiving messages. Because well, the idea here is that why it is strongly suggested is that we should actually block the receiving behavior until we receive a message, because otherwise, if it is active, if it is checking, if it is executing in a loop and checking for new messages all the time, it will exhaust all the resources of your computer. So that's why we should block it, and block is actually means that we just stop the behavior until a new message comes. Okay, this is how Jade agents are compiled and run. An example for Tamagotchis again. And this is how it looks like. So this is the Tamagotchi prototype. So for the situation where there are no Tamagotchis yet, someone has come up with a brilliant idea to create this kind of digital pet and has created a prototype. And now is about to demonstrate the prototype to a venture capitalist. Okay, this is how it looks like. And as you can see, here is the start visiting. This is how it is simulated. And here is the user interface for a Tamagotchi. The Tamagotchi telling I am unhappy, then connecting with another Tamagotchi, message sent to the other one, could I come to your place, received, please come. There are actually agents behind it. I mean, it is not just one application, but there are different agents representing these two Tamagotchis. One for the first one who is going to visit, and the other one for the second one who is hosting the visit. Received, please come, they're printing away. Sent good day, received hello, gave a present food, received thank you, sent may I play with you, received okay, play, gave a present chocolate, received thank you, sent may I play with you, received okay, play, gave a present toy, received thank you, sent may I play with you, okay, play, may I play with you once more, and then back home. So this is an example of a prototype for Tamagotchis. And finally, just I mentioned that there is one host or one computer is devoted to managing. Well, not just to managing, but the managing is always performed from one computer. But that computer can run also other agents, not just this Jade remote monitoring agent. That is an agent by the Jade system that takes care of managing the overall multi-agent system. And this is how it looks like. These are different containers and different agents running there. And this is an example of a sniffer agent. By means of a sniffer agent, you can actually sniff the interactions between different agents in your system. So this is an example of interactions between different agents. I mean, what kinds of messages and when they have exchanged. Okay. And that was about Jade. I am sorry it was quite technical, but this was actually the plan for this course. To become technical later on. So to show you that we, in addition to just creating a business plan, in addition to just modeling and designing our products, we also need to prototype our products, and we need appropriate platforms, appropriate technologies for prototyping. Okay, let's wrap up now. Not just this day, but in general. Let's wrap up, and this means we will be finished on time by lunch. So first conclusion I would like to emphasize here is that modeling is important and fun. I mean, it's not. It doesn't work in the way that you just come up with a brilliant idea, and then you create a business plan, and then you just program your idea, implement your idea, and it's all done, and you will be rich. It doesn't work this way. You need to conceptualize your idea, you need to model it from different perspectives, focusing on interactions, knowledge, behaviors of different components of your system. And after that, based on these models, you need to prototype your idea. And only after developing a successful prototype, then actually you can be confident that this idea at least can be implemented. And another thing is that if a venture capitalist agrees to fund it, but you can show at least to the venture capitalist that this can be done. And the rest is now up to how well you convince him or her. So modeling is important and fun. Agent-oriented modeling facilitates rapid prototyping. It's a one way how to actually proceed from your product idea to your business model, from your business model to your product model. So this is what we have been doing here for 1 week. We have been modeling your wonderful products. So to the product model, and from the product model to the fast prototype of that product. And a rapid prototype is not a real product. So please bear in mind that a rapid prototype that you should end up with, it is not a real product. A real product will be implemented in different ways. I know it from my own hand because I've been involved in developing many rapid prototypes in Finland, Australia, Estonia. So the rapid prototypes can be developed by using software agents, for example, very easily. But when it comes to developing a real product, then probably we'll use different technologies, even though I think agent technology still can be useful, even for developing real products, especially for developing social products. It can be useful because it's based on peer-to-peer paradigm, but still your rapid prototype is not your real product. And one recommendation, consider hybrid peer-to-peer architecture. You remember the one with peer-to-peer interactions and server in the middle and also software agents for social applications, because it's more natural. It more naturally fits into this paradigm of social applications, paradigm of people interacting with each other, exchanging information. It's more natural compared to client-server approach. Okay, and now finally I'm coming back to this yesterday's suggestions for pitch talks. My recommendation is to start with the goal model, what the product does. So you address the question what the product is about to do. Then business model, how to make money with the product. And final example of using the product by some customer or stakeholder. So this is my idea. How it could be done. So that's it. I think there will be another wrap up this afternoon, both by me and by Mr. Alarkoil. But this concludes my course. So many thanks for your attention. So it has been a really pleasure. It has been fun actually to do it, and I have learned a lot while doing it. So thank you.